Turn on this computer. Okay, great. So today the lecture is about time series. So before I start, I would like to make an announcement that I decided to assign an office hour, which will last for 1 hour after this lecture. Sorry, 1 second. Yeah, so it's going to be from 11 a.m. Eastern time to 12 a.m. Eastern time, right after this lecture and all the following lectures. So if you have any questions about homework, about lecture material, about anything, please stay after this and ask me, and I'll be happy to answer. Okay, so this is outline for the lecture today. So we are going to talk about what is time series, some of the traditional algorithm for time series, and also some attention-based algorithm for time series. Okay, so what is a time series? Time series is a series of data points indexed by time. The data is in the form of Ti, Xi, and as you can see, I put it here that Xi is actually a vector. So the length of this vector is what we call the number of expected features in the time series. So Xi could be a scalar, which means we only have one expected feature per time index, or it could be a vector, which means we have more than many expected features per time index. Probably the most popular, well-known time series in our daily life is the stock market. So in this case, the Ti is the past or the current times. And then Xi could be, Dow Jones, NASDAQ, or individual stock price, or even a linear combination of them. So language can also be treated as a type of time series. In order to do that, we will need something called a one-hot encoding of each word. So suppose we have a dictionary which only contains 4 words. This 4 word is I love machine learning. So what we can do is that we can convert each word into a vector of 4 elements. For example, I correspond to 1000, love correspond to 0100, and machine learning, blah, blah. So, and then we can concatenate the 4 words into a 4D, into a 2D array. Then this sentence, I love machine learning, can be represented in this form, which is 10000100, etc. So this is what we call a time one-hot encoding of wording. So in this way, the text data will also follow this Ti-Xi structure. Now Xi is a vector of length 4. And Ti, well, in this case, the time is a bit ill-defined, but it still makes sense because text is also ordered. The machine learning field that's dealing with text and sentence is called the natural language processing. Most time series algorithm can also be applied to NLP and vice versa. So in this lecture, we will focus on numerical time series, which is most related to germanium detector, and we will only occasionally use NLP to help the understanding of concepts. Okay, so now let's talk about how time series is kind of embodied in physics, especially experimental physics. So I guess most of the participants of this class come from a germanium detector background. So definitely germanium detector produce a waveform, which is a very typical time series. Ti in this case is a time sample, and Xi is a corresponding ADC counts or voltage if you convert the ADC value into an actual voltage reading. So usually what we do is that we feed in waveform one by one into our machine. So the number of expected feature is just 1. So we have 1 ADC count or voltage per time sample. However, we can increase the number of features by performing some kind of waveform reshape. For example, if your original waveform contains 3,000 times ADC count per in 3,000 different time samples, you can actually reshape it to 1,000 time sample, and each time sample contains 3 ADC counts. So the reason we might want to do this is because long time series are usually expensive for our RNN-based model that we will introduce today. So this is just a useful trick to reduce the length of your time series. So in liquid scintillator and water Cherenkov detector, what you can do is that you can stack your PMT time and charge into what we call the scintillation time profile, where the x-axis is just the time of the PMT hit, and the y-axis is just the charge the PMT registers. And then this also become like a waveform-like time series, and you can use a recurrent neural network to analyze this scintillation time profile. This plot is actually from one of my colleague, Takeuchi-san. He showed this on Neutrino 2020. So the downside of this approach is that it gives up all the positional information in the liquid scintillator detector, which actually contains a lot of information. But it is possible to also treat liquid scintillator water Cherenkov detector data as time series. So the last time series in physics is actually used in LHC. So this is a very interesting talk I heard about two years ago. They are talking about they are treating each particle track or jet as a word, and then they are comprehending the track and jet to backtrack the physics process using the recurrent neural network model. So I think this is a very interesting approach. But I don't have too much plot or anything to show on this slide. Okay, so there are two types of time series. The first type is called homogeneous time series, where the interval between each ti and ti plus 1 is always constant. So here on the bottom, I show the blue dots are a homogeneous time series. There are also another type called the inhomogeneous time series. The idea is that the interval between ti and ti plus 1 varies, so they are not always constant. They are not always the same interval. In the machine learning algorithms, there is no particular good way to deal with inhomogeneous time series. The usual approach is to kind of do some kind of interpolation and convert it into a homogeneous time series. But thanks to our constant DAQ sampling rate, our waveform is homogeneous time series, and we don't need to worry about this inhomogeneous behavior in T. Okay, so now I would like to talk about two important features of time series. So the first important feature is the order of the time series. Order contains actual information that mirrors the values. Even if two of the xi contains exactly the same, even if two of the time series contain exactly the same number or exactly the same words, they are different if the order are different. So for example, this if you consider the two sentences, woman dance well only for a little while. For a while, only little woman dances well. They contain exactly the same word, but the order are different, and the two sentences convey completely different meaning. The other important feature is a long-range correlation. So if you look at this Shakespeare's quote, it says, "Love looks not with the eye, but with the mind, and therefore is when Cupid painted blind." So the first sentence, "Love look not with the eyes," and the last word, "blind," they are actually correlated. They are actually kind of a metaphor of the same thing. But you can see that they are very far away in the sentence. One is at the very beginning, one is at the very end. So you have to capture, so we human beings, we are very well trained to handle long range correlation. So when we read this sentence, we know that this first phrase and the last word, they are correlated. But machine learning models are not. They are like infant that doesn't know anything. So a good algorithm, a good machine learning algorithm for time series should handle these long range correlations during the training process. So basically, a good algorithm for time series should handle both order and long range correlation properly. Okay, so this is the first kind of a submodule of this module. So I prepare this as again as a little rest time, and also I prepare a question. So what is the biggest shortcomings of the one-hot embedding or one-hot encoding of word we discussed about in natural language processing? Does anyone want to try this question? Or if you have any other question, please feel free to ask.
So the answer for the question on the screen is, if you have many words, then the number of the dimensions explodes. So you have as many dimensions as the words you want to one-hot embed, right?
Yeah, that is correct. So let me go back to that slide. Yeah, so Sasha make a very good point. So in this case I showed, I only have 4 words. So my dictionary only contains, only contains a vector of 4. But what if you have 1,000 words or even 10,000 words? Then each word is going to be represented by a dictionary of is going to be represented by a vector of 10,000. And at the same time, you will see that each of the vector is highly sparse. So only one unit contains information. All the other units, they are 0. So this makes, especially if you have a very long vector, then this vector, although it contains a lot of elements, it doesn't really convey you too much information. So that's something we would like to avoid in the natural language processing domain. And we use a technique called token embedding, but I'm not going to talk about it here because it's kind of irrelevant to what we are doing. Okay, great. Let me go back.
I have a question.
Yeah, go ahead.
So in case of stock market, I think the final, well, the goal is very clear. That is to predict the next point, whether it will go down or go up.
Yes.
In case of I love machine learning, what is the final goal?
So it depends on what kind of natural language processing task you would like to do. For example, you can do machine translation. So translating a sentence from English to Chinese or to German.
But how would this technique help? I mean, or put it more concrete, what is the minimization? What is the loss in that case?
So you are talking about a machine translation task.
Yeah.
Okay.
So no, actually, I'm not. I don't have to. So what I want to say. So, for me, it is easier to understand it if the task is clearly defined. So that's why I start with the stock market. That's why we learn from the past and we try to predict the future. Okay, let's don't talk about the language. Let's go to the waveforms.
Sure, the stock market or germanium?
No, sorry, the germanium waveforms.
Okay.
So I guess the goal is to separate background signal from background.
Yes, yes.
And how would this time series approach help that? How do we define the loss?
Well, basically, the inputs, so each germanium detector waveform is a time series. And you can feed a time series into a neural network, which we will talk about in the next submodule, actually. And then you can use the same loss, the classification loss, which is a cross entropy loss, to do the classification just the same way as you are doing classification for cats from dog. So that's the same, but you are just changing your lower part of the neural network to handle the time series data.
Or let's put it this way.
Maybe I can. So actually, it's like the machine actually knows the meaning of the sentence. At least it knows this sentence is a good sentence or a bad sentence. How about that? So the machine actually knows the meaning of the waveform. It's a bad waveform or a good waveform through
Yeah.
Okay.
Yeah.
So then you have to give a definition. What is a good sentence? What is a bad sentence?
Yes, it's going to be a supervised learning, just like the CNN. So in that sense, the big structure doesn't change. It's just the structure of the network changes.
Okay.
Yeah.
So in case of waveforms, then so we give the neural network good waveforms, our signal. We give it many times. And we also feed it with bad waveforms, and then the neural network will give us 1 and 0.
Well, it gives us a number between 1 and 0, which is like a probability.
Okay. And then we tell neural network whether it's correct or not, and then the weight matrix will be updated.
Yes, exactly. Yes.
And then after that, we can do it.
Yeah.
Okay. Then, but why do we have to use a time series for the waveform?
Well, so, it's not like we have to use, but it is our data is time series, right? I mean, waveform is a time series. Just like, image is an image.
Okay, I got it. Yeah, thank you.
Okay, actually, give me 1 minute. I will get some water real quick. All right, let's keep going. So now we will talk about the possible models that we can use to handle time series data. Well, of course, the first thing we want to try is fully connecting neural networks. So for time series data, using a fully connected neural network is not as bad as image data. That's mainly because time series is not as sparse as image data. So in germanium detectors, the data and also the data set size is also smaller. So in a germanium detector data, the data size usually we have 3,000 time samples per waveform, which is actually a reasonable input for a fully connected neural network. Remember, for image data, we usually have 1 million or even 10 million inputs per image. So that's too large for a fully connected neural network. The downside of fully connected neural network is that it does not particularly handle the order of the data. And also it's hard to train the FC network to gain long-range correlations, as we discussed in last sub-module. Another approach is to use a convolutional neural network. So 1D convolutional neural network handles long-range correlations well. So remember, we talked about this concept in last modules. So one convolutional layer calculates the spatial correlation within the filter range. So it calculates by using the filter to go through the entire image, or in this case, the entire time series. The correlation amount of the value within the filter are actually adopted. So by stacking many convolutional layers and optionally using a pooling layer, we increase the reception field of the convolutional layer and eventually let it cover the entire time series. So in that case, you will actually be able to handle the long-range correlation. I actually, if you want to use this model to approach time series problem, I actually have a tip. So with my own experiment, I find that large kernel size works well for the waveform data that we are dealing with. CNN is robust and easy to build, but the order information is still missing because CNN doesn't really understand that this element comes prior to this element. So CNN can be enhanced to handle order information using something called positional encoding, which I'm not going to discuss this week, but I'm going to actually discuss next week in time series 2.
Yeah, may I ask a question right here?
Yeah.
So this is my understanding from your previous lecture about the convolution neural network is actually it takes into account the spatial ordering because you basically move the filter from one side to the other side. So in that case, the weight or the information always has some overlapping. So let's see, we have a big picture like this, and then you move your filter this way, right? So you always have the overlapping part where you take into account the information from the previous spatial, the previous portion of the whole picture. So because of this overlapping, your weight actually contains part of the previous information. Is that right? Is my understanding right?
Yes, but I think that's not all the order we are talking about. The order we are talking about here is that it knows this is the first, this is the second, this is the third.
Yeah, sure. However, let's say if the picture is very long, let's say we have a very long picture. In that case, our filter only moves this way. We don't have to move up like downwards. So let's say we have a very, very long picture.
Yeah.
And then we have our filter moving this way. That's effectively the same as taking into account the old information to update your weight.
Okay, this is a very subtle. Yeah, go ahead.
That's the same as time series neural network. I mean, the basic idea is to use the old. So basically, the order is already built in.
Okay, so this is very subtle. So it could be hard to understand, but what you showed, Jing, is it knows. So basically, the idea is that CNN is equivariance to spatial translation. So, but it still doesn't know that this first patch your filter scan is in the first location. The locational information is not there.
The first location.
Yes.
Okay, so
it
we
doesn't
use
know-
the information to update the weight, but the neural network does not know that's the first place.
Yes,
Okay.
yes. It doesn't know that's the first place. Yes. So that's the idea. So
Okay, yeah, let me think about it.
okay, yeah, it's a very subtle point. So yeah, maybe if you will also attend the time series 2 when we discuss about positional encoding, this will be more clear, hopefully.
Okay, thank you.
Okay, so so the canonical model for time series and natural language processing task is what we call the recurrent neural network, which we will discuss mainly discuss in today's lecture. So remember, each xi of the time series is fed sequentially into what we call a recurrent unit. And the recurrent unit contains a hidden state, which we call hi, which store information from all the previous inputs. So, and what information to store in the hidden state hi is decided by the training process. So for example, if we are moving to this xt points, so what we do is that RNN has two kernels. One is a weight for the input and one is a weight for the previous hidden state. So W input is a, yeah. So what, okay, so I'm actually talking about. So when a recurrent unit goes to the current point xt or xi, I label it here. So the kernel is multiplied to the inputs and also the previous hidden states xi and also the previous hidden state hi minus 1. And then
what is H0?
Sorry,
What is
H0.
H0?
Oh, H0 is a initialization of the hidden state. So it's just a whole bunch of random number.
So let's look at the first. Yes, the first, this one. So if this is a 1, this would be 1. This would be H0.
Yes.
So you are going to assign a random number here.
Yeah, just assign random initialization to H0. Yes. And it's going to change during the training process because when we go to H1, H0 is going to be, as you mentioned, it's going to be W input times X1 plus W hidden times H0 plus a bias. So H1 now is a different number when you go to the next time index of the time series.
I do not understand the physical meaning of H0. So H1 is easy to understand. It contains the information from the previous time sample.
Yeah.
But then H0 does not contain any information. Do we really need it? Or should we just give it 0?
Well, if you don't have H0, then you don't have H1, right? Because you are using the same recurrent unit to slide through your entire time series. So there must be
H1. So let's say this one is gone, we still have H1.
Yeah, but now you cannot use H1 to the next unit, right? Because it's the same unit. So in your next step, you are doing W input times X2 plus W hidden times H1.
Yeah, but H1 has been defined.
Sorry, pardon?
So H0 can be 0, but H1 is not 0 because H1 can be calculated using this equation. And then H1 can be used here for H2.
Yeah, that's right. That's the recurrent process, yes.
And what I want to say is that it looks like H0 can be 0 because there's no...
Yeah, you can initialize it to 0 if you want, yes. It depends on what you initialize it to, yeah.
Okay, thanks.
So information from the previous hidden state hi minus 1 and si are analyzed together. So that's the beauty of this model. And the outputs hi is produced by an activation function. Here we usually use a hyperbolic tangent, where we say, so the hyperbolic tangent, and then the hyperbolic tangent of hi prime is hi, and then we output hi as what we call the intermediate hidden state output. And also hi is a hidden state output is h to the next recurrent step. So we let this iteration keeps going until the end of the time series, and the last hidden state output hn is output of the network. So remember, in convolutional neural network case, we flatten the feature map of a convolutional neural network and we feed it into a fully connected neural network. So in this case, what we will do is that we will feed the HN into a fully connected neural network. RNN is recurrent because the output of previous step is fed into the current step. So that's what we mean in like a recurrence by the word recurrent. So RNN handles order information well because it's going through the entire time series in order, but it has the following shortcomings. So first of all, long-range correlation is not handled very well. Technically speaking, HI should contain information from all the previous I-1 indices. But, and HN, HN would contain the information from the entire time series. However, during the actual training process, we find that the long-term information is often flooded by long-term information at xi is often flooded by near-term information from xi-1 and xi-2, just because near-term information is more emphasized compared to the information at say x0 and x1. The other disadvantage is that recurrent neural network is not parallelizable. Each step requires input from a previous step. So if you want to train a very large model using recurrent neural network, it's almost not possible because you have to wait for the previous time index to train before you can train the first with the current time index. So to deal with the long-range correlation loss in canonical recurrent neural network model, we propose a new model called long short-term memory network. So LSTM is proposed to embody RNN with long-range correlation. So instead of having just a single hidden state HI, LSTM actually contains two hidden states. One is a hidden state HI and the other one is a cell state CI. So in this case, HI will correspond to what we call the short-term memory, and CI is what we call the long-term memory. So because of this, LSTM actually have 4 times 2 kernels. So we have one pairs of kernel W input and W hidden for 4 gates, which is an input gate, for get gate, cell input gate, and output gate. We will talk about what this for is in the next few slides. And we have no kernel for cell states because we do not want to directly modify cell state. Remember, cell state represents the long-term memory, and we want to keep the long-term memory kind of constant, and we don't want to directly modify it. The long-term memory cell state will only accept or reject information indirectly through what we call the gate operation, which we will talk about in the next slide, to preserve the long-range correlation of the time series. So a gate operation is a structure to control the information flow between the long and short-term memories. The essence of gate operation is a sigmoid activation function. So remember, a sigmoid function can convert any input into output value between 0 and 1. So if you multiply sigmoid's outputs into certain say a certain vector, then this will allow the sigmoid output to decide whether to preserve or reject information in this vector. For example, if the sigmoid output is 0, that means the information at this position should be completely erased. So whatever the original value is, it got reduced to 0. If the output is 1, it means the information at this position should be completely preserved. That means if the original value is...
Let's confirm that. When you say erased and preserved, what do you mean is that whether this piece of information will be transferred to the C branch, is that right? Whether the C branch will use it or not?
No, it's just, for example, if you have let's just use a single value. So if you have a value 7, which represents some kind of information, if the gate give you a 0 and you just multiply 0 to 7, now you get 0. It means that 7 just disappeared.
I don't understand what disappear means. It means that you don't use it in this branch.
You want to forget it. You want to erase it. Yes. That's so what I get by erasing it.
This branch process all the single samples, the time samples, but some of the time samples will survive to the long-range memory branch.
Some of the information from the time samples will survive. Actually, Jane, I haven't go to there yet. So here I'm just talking about how gate operation can preserve or erase information. So I haven't started talking about how we process each time sample yet. So, so the point is that I just want you to understand that by multiplying the sigmoid output or the gate information to certain vector, it doesn't have to be, I mean, at this point, it can be arbitrary vector. The idea is that we can decide we want to erase information if the sigmoid output is 0, or we want to completely preserve the information if the sigmoid output is 1, because if you multiply 1 to something, you doesn't change it. It's the same. If you multiply 0 to something, then it becomes 0. So that's
so you two are talking about the same thing, I think. It is just 0 in C branch, as Jing said. That's what he meant by erasing it. You get an output of 0.
Okay, yeah. Okay. Yeah, so I will keep going. So one more point, which could be somewhat counterintuitive, but fractional output is allowed, meaning that we want to partially preserve this information. So for example, your sigmoid value can be 0.3, and you multiply 0.3 to 7, you get 2.1. That means you want to keep probably like 30% of the information. So that's the idea of the gate operation. And we will use this gate operation to define our LSTM network. So, okay, so what we do is that we will define the following symbols. Where a hidden state HI type is the weight matrix of type, the input weight matrix of type times Xi plus the input weight matrix of the hidden state times the hidden state plus the bias. So this is actually the same as the equation I showed in the recurrent neural network. But now, because we have multiple gates, we have to define a certain type for each of the gate. For example, when we are talking about forget gate, we have this HI forget, which comes from the weight matrix of the input of the forget gate times the input, plus the weight matrix of the hidden state from the forget gate times the hidden state plus the bias. So forget gate. So in the forget gate, what we do is that the H forget will act as a gate to erase information from the long-term, from the cell state, which is the long-term memory. So the current input and the previous hidden states will jointly decide by feeding it through a sigmoid function. We use the gate operation to jointly decide what information can be preserved in the cell state and what information we should erase in the cell state. Then we feed it, then we go into an input gate where we input information into the cell state. So in input gates, each input acts as a gate to control each cell input. So hyperbolic cell input produce values between -1 and 1. And when we feed each input into a sigmoid function, it's going to give you a value between 0 and 1. So you multiply this value between 0 and 1 to a value between -1 and 1. So this is going to give you the amplitude of the information you want to input into the cell state. So basically, it tells you what value you want to add or subtract to the cell state at the corresponding location. So basically, here the location is xt. Note that each input and each cell input are different since they are corresponding to different kernels. So when we do each input, we use the input weights to multiply the hidden state and the current input. And when we calculate the cell input, we use the cell input kernel, the cell input weight matrix, to multiply to the input and the hidden state. So up to this point, the cell state for the current timestamp has been produced. So it will remain unchanged until we iterate to the next time sample of the time series. And eventually we have the output gate. So the output gate structure is similar to the input gate, but now the input is calculated from the cell state. So we take the cell states, we put a hyperbolic tangent activation function over the cell state to produce a value again between -1 and 1, and then we use the outputs. We use the outputs. We use the output gate to control the value, to control the hyperbolic tangent cell state value, and then we multiply it together, and this will decide the value to add or subtract to the intermediate hidden state output. And then we output this as an intermediate hidden state, and again, we output it to the next recurrent step, to the next input. So LSTM preserves a long-range correlation because the cell state is isolated from the recurrent process. Its information can only be indirectly added or removed via the gate operation, but we are not multiplying any kernel to the cell state to directly modify its value. The forget gate throws away only important information from the previous cell state, which allows a flooding of information from the previous step. The input gate only allows selected information to flow into the cell state. The intermediate hidden state output is calculated from the cell states and only indirectly affected by the input and hidden state via the gate operation. So for more information, I would actually recommend you to read this blog about how LSTM network works. Okay, so this is again our second submodule, and because I think there are a lot of material, so I didn't leave any discussion question. So if you have any question about the previous module, please feel free to ask.
So I feel like that the C branch is only basically downsampling of the original information. But this downsampling is not supervised, or you can say you let the machine to learn which information, which sample should be thrown away.
Exactly.
Right?
Yes, that's the idea. Yes.
Okay, thanks.
And also you can modify the input by multiplying the weight kernel to it, right? Because we have this weight kernel where we multiply through original information. So it's not directly what we read in the waveform, but actually this value multiplied by certain kind of weight. So that's what we use to modify the information in the cell state and the hidden state.
Oh, okay, that makes sense. Thanks.
Okay, we will wait for maybe 1 more minute, and then we will go through the last submodule.
It would be nice if we can make it clear what is the difference between the convolutional neural network and the time series neural network, the recurrent neural network.
They are, I feel like they are completely different. You are talking about what's the difference when we use this two model to handle time series? Is that your question, Jing?
Picture, it only has one row of pixels, but in this row there are like 3,000 pixels. And in that case, yeah, then you use a convolutional neural network. You can also go through it. The information from the previous cells will go into the next one. So this way, I don't know why there is a huge difference between these two methods. Just in case in case of processing waveform data.
Okay, so first of all, convolutional neural network is invented for image. So the original design purpose is different from, and recurrent neural network is invented for time series and language processing. So the original motivation for the innovation is different. Secondly, I think I never say that recurrent convolutional neural network would perform worse or anything than the recurrent. So they are actually both viable methods to try on a time series. Actually, I think usually when we try to deal with time series data, we use both models. So I don't think time series CNN is going to perform worse than RNN. But RNN is just a more canonical approach to time series data because it's kind of invented for this purpose. I think that's the only difference. Yeah.
Okay, thanks.
Okay, great. We have 18 minutes, so I think we will just keep going to the last part. Okay, so I will just do a very quick review of RNN. So recurrent neural network takes a sequential input, which is what we call the time series. it exhibits a hidden state containing information from all the previous steps. And each step will output what we call the intermediate hidden state here, and then also output this intermediate hidden state to the next time step. So when moving one step forward, the previous intermediate hidden state ht-1 and the current input xt are jointly analyzed using some either simple or complicated mechanism. The final hidden state hn contains information from the entire time series will be fed into, for example, a fully connected neural network for further analysis. So long-term memory is a more complicated version of RNN, but structure of intermediate hidden states and final hidden state still preserved. So here, I will start talking about attention-based mechanism. And before we start, I would like to give you a kind of analogy of what attention is. So this is a picture of the Tron balloon. So when we use a machine, say, for example, a convolutional neural network to analyze this image, it's going to scan a filter throughout the entire image, and then it's going to capture some feature, right? It finds a tree here, it finds a church here, it finds a human, some people here, it finds a cell phone here, and then it finds a balloon. So the machine scans every single pixel of the image, and it detects many objects. But the machine does not know which object is the most important for the image. In other words, the machine does not know where to put its attention on. But as human beings, we are very well trained. And when we look at this picture, we know, oh, this picture is about the balloon. But it's not about the church. It's not about people holding the cell phone. So we are well trained to know the theme of the photo with the first glance. And the mechanism behind our thinking is what we call the attention mechanism. So we also discussed about the long-range information loss in a time series data. So as you can see, if you feed this waveform into your recurrent neural network, you have this baseline part, which doesn't contain too much information. You have this you have this rising edge part, which contains most of the information. But following that, you have this falling edge part, which does not contain a lot of information either. So when you feed this waveform into the recurrent neural network, you only use the final hidden state output, but you basically kind of throw away all the intermediate hidden state output, and that's actually a huge waste of information. So the idea of attention mechanism is to utilize all the intermediate hidden state output to perform your task. And I would call this call the attention mechanism one of the most important invention in the history of time series and the natural language processing. So the idea is that you calculate the similarity of each hidden state of RNN to the final each intermediate hidden state of recurrent neural network to the final hidden state. And if you use you can use several type of similarity metric to calculate this similarity. So the different similarity metric will define different type of attentions. And if you do a weighted sum of the concatenation result and you use a softmax to produce an attention score. So this will look very confusing at the first glance, but we will actually do a detailed breakdown of this process. Okay, so let's first talk about the type of attention. So as I mentioned, the type of attention is defined by the similarity metric we use to calculate the attention score. So given each hidden state's vector hi equal to 0, 1, 2, 1, 2, 3, blah, blah, all the way to -1. Remember, that's our intermediate hidden state. And we also have the final hidden state vector hn, which contains ideally the information from the entire time series. What we want to do is that we want to produce a scalar quantity to measure the similarity between the final hidden state vector hn to each of the intermediate hidden state vector hi equal to 0, 1, 2, blah, 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 all the way to n-1. So we can do this using several metrics. It's probably the easiest one to do is just to do a dot product between hi and hn. We can also do something like a cosine similarity where we do this hi times hn divided by this. So this is actually the cosine of the two. But actually the way I prefer the most is what we call the weight kernel concatenation. So the idea is to multiply hi to a weight matrix and then multiply this weight matrix to hn. And the W is actually a cell-defined kernel tensor. So its value changes when we are training the machine learning model. So this is this multiplication is also going to give us a scalar. Sorry, I think something is wrong with my slide. Okay, so the attention score. So remember, we produce a S for each pair of HI with the last hidden state output HN. So the attention, so after producing this scalar quantities, we can feed it into a softmax function to convert into what we call the attention score. So the idea of a softmax is that no matter what values you have in this tensor, after you feed this through a softmax function, the sum of this tensor is always going to be 1. So the attention score can also be treated as some kind of a relative weight or relative probability of each intermediate hidden state. And what you do, and the last step is that you produce a so-called context vector by multiplying the attention score to its corresponding hidden states, and you sum them up together into one context hidden state. And attention vector is obtained by concatenating the context vector together with the last hidden state output HN. Okay, so why attention mechanism works? So let's say we have a waveform inputs. Well, for simplicity, I'm just using this 7 block to represent 7 timing indices. But in the actual waveform, you will have 3,000 indices. So ideally, the last hidden state output HN should have already contains all the information we need about the waveform. But because of the information overflood, it often loses focus to the most critical part of the time series. For example, this HN might only contain information from the very end of the falling edge, but it actually forget about the rising edge. So in order to avoid that, we use the attention mechanism to allow the final hidden state HN to talk to each of the intermediate hidden state HI. Is a feature in one hidden state, for example, H3 in this case, which contains a rising edge, is very important, then the final hidden state should contain most of the information from this hidden state. That means if you calculate the similarity from H3 and HN, it should give you a very high output because they are very similar. So this will lead to a high attention score in the hidden state H3, HN, and low attention score to other part of the waveform. So by doing this, you are actually forcing your machine to zoom in to the rising edge of the waveform while kind of trying to forget the unimportant information in the noise floor or the falling edge of the waveform. Okay, so when we have the context vector, we can actually proceed to the next step using the context vector. So what we usually do is that you concatenate the context vector and the final hidden state into just a 1D vector. And then you feed your 1D vector into the fully connected neural network for either a classification task or a sequence-to-sequence model, which we will talk about in time series 2 for machine translation. So this is basically the same as a convolutional neural network case, where we stack a whole bunch of convolutional neural network as our feature extractor, and then we flatten the final output and we feed it into a fully connected neural network for the classification decision. Okay, so another important application of attention score is the interpretation of the machine learning algorithm. So we know machine learning algorithm is most of the time a black box, which means that we don't know where it is looking at. But attention score actually tells you where the neural network is looking at. So if part of the waveform has a high attention score, that means the machine is putting its attention on this part of the waveform. So we have an attention score assigned to each one of the or few of the time sample index. And as I mentioned, high attention score means the time segment is more important than the others. So so on the right, I show the plot of attention score of a trained waveform classifier on a fake germanium detector waveform. And we can see that it correctly put attention on the rising edge. So high attention is this magenta color here, and low attention is a cyan bluish color here. So you can see it successfully put its attention on the rising edge of the waveform while leaving the noise floor and the falling edge of the waveforms not attended. Okay, so this is a lecture. So in this lecture, we discussed what is a time series, and we discussed the type of time series, and also the time series data we use in physics. And also we discussed the features in the time series. And then we discussed the RNN-based time series model, which is vanilla recurrent neural network and long-term short-term memory. And we also give a brief intro to the attention mechanism. So next time we'll discuss more about attention-based algorithm for time series in time series 2. So that is everything in the lecture. Is there any? So Wenqing, I see you have questions and you raise your hand. Do you want to go ahead and answer?
Right. So when you mentioned the attention mechanism, that makes me wonder. So is it true that the number of hidden state is the same as the number of input words, for example, or values in the series?
So it really depends on how you define your input. So for example, I think as I mentioned very early in this talk, a waveform, for example, it contains 3,000 time samples. So if you input this waveform in the form of 3,000 time samples and 1 feature per time sample, then you have 3,000 hidden state. But if you reshape your waveform so that it contains 1,000 time sample and 3 features per time sample, so this is equivalent to downsampling the waveform, then you will have only 1,000 hidden state.
Right, but in principle, the fourth hidden state here has all the input of the first 4 blocks. The third hidden state here only has the input from the first 3 time series input.
Sorry, I don't really get that. The first block. So if this is the first hidden state, then it only contains a hidden state from this region of the waveform. So it's pure baseline.
And how about the second hidden state? Doesn't it contain both the first and the second?
Exactly. The second hidden state will contain the information from the first hidden state and the second hidden state.
Right. So it's accumulative. So my real question is that then it is pretty hard to actually say one input at a certain point in the series actually can change the hidden state by much. Because it's accumulative, even there is a big change, it might not be able to change the average over the previous cells.
I actually doubt that. So if you think about the germanium detector waveform case, for example, you are trying to separate single site from multi-site. So when you are feeding your single site and modified waveform into a neural network classifier, then their baseline is going to look the same if you are extracting them from the same detector.
Right.
So
exactly.
So the hidden states is even though they are cumulative, is not going to find anything different from just this baseline oscillation. So there won't be too much information being introduced in the hidden state, even if you go all the way to H2 here.
Okay. Okay. All right. So basically, my understanding is correct. It's just the impact probably is big enough for the network to find that's attention to pay there.
Yeah, exactly. Yes.
Okay. All right. Thank you.
Okay. So this is very interesting. One thing I do not understand is that how do you give feedback to your neural network to tell it which part is more important? So let's just look at the most fundamental neural network. You always use the loss to tell the neural network to update its weight.
Yes.
So basically you give it a feedback.
Yes.
In case of attention training, where the feedback is given.
So remember, attention mechanism only contains a weighted kernel. Here, this slide. So you see, if you use this weight kernel concatenation, you also give it a W. So this W can change during the training process.
Yeah, I understand you have to have something to tune, that's for sure. But you need to get feedback so that you tune it.
Oh,
right?
yeah.
So how the feedback is get into the picture here.
I guess you are talking about the loss, right? I mean, you just calculate the loss in the final output of the. So remember, we don't just build a network based on the RNN. We also need to put it into a fully connected neural network. And the fully connected
so you're saying that
single number.
The training of attention weight and the training of the weight for the neural network is using the same laws?
Yeah, exactly. Yes. I mean, that's how a neural network model is built. So all the weights are trained simultaneously using the backpropagation version. I mean, that's the beauty of the backpropagation, because it allows you to tune very, very complicated laws. I mean, we have been discussing very complicated models so far, and it has hundreds, thousands of different laws in the weight matrix. But using backpropagation and the optimization and stochastic gradient descent, you will be able to upgrade it correctly to perform your job. I mean, that's the beauty and the power of a machine learning model.
Okay, thank you.
I have a follow-up question on this. So it seems that the attention score can also be used in combination with CNN, because then you can decide which filter output is the more important one.
Okay, that's an interesting. That's actually a very interesting point. But if you use it in CNN, then what is your last hidden state output when changing? It's ill-defined, right?
Right.
Yes. So when you calculate the attention score, you are calculating it between the last hidden state output and every single intermediate hidden state. Well, in a CNN model, you have every intermediate hidden state, but you don't have the last hidden state.
Okay, I think you actually answered this pretty well. I was wondering, basically, I was wondering why the neurons in RNN haven't they already included this weighting attention score just like in CNN? But I guess you are right, because of this last hidden state. It is different from CNN. I guess in CNN, basically all the neurons already carry the weighting information for the filters. But here you need additional stuff to do explicitly that, and that is the weight curve score. Okay, gotcha.
Yeah. So I think a lot of time, so theoretically, just like universal approximation theorem says, we can use a 3-layer fully connected network to deal with anything, but it's not possible to actually train such a model. So in this case, it's also like the attention mechanism is trying to enhance the performance of RNN. So although theoretically RNN should contain all the useful information, but it's very hard to train without these kind of mechanisms.
Right. Yes. Yeah. They care about the performance in terms of many things, including computation time. Yes. I guess I got it. Yeah.
Okay, great. So Sasha, you have a question? Do you want to go ahead?
Yep. Can we go to slide 32?
32. Okay, 1 second.
No.
Here. Okay.
Yep. So let's say that all the system got most of the information in this cell. Okay, that's an unfortunate color, but I hope you see it. And when we move to the next cell, well, the information from the previous one should be preserved. When I'm here, the information from the previous one is preserved because there is an important information which we want to drive all the way to the final state, right? So the information from this this one, we carry it all the way until the end, right?
Yes, the information. Yes, if you do not,
okay,
it's gonna decay. Yeah.
Yeah, since it's important information, yeah, we want to drive it to the very end of the system, and then I don't understand when we can take the similarity scores between the last cell and this one, we saw a high score, right? Why isn't it high for this pair? This guy here, it still contains all the information from the previous one because we want to preserve it. So how did it happen that the similarity score of this pair was not high also?
So I think the reason is because the attention score is calculated based on the intermediate hidden state. So remember, we are trying to project the final hidden state to the output right after we see, you can see my cursor, right? Right after
yes.
this rising edge. Then if you compare this, although the RNN allows it to contain information from the previous hidden state, but because as you mentioned, the information will decay, then this becomes less important compared to intermediately the output of this hidden state. So the attention score for this is going to be higher than the attention score of this one. And during the training process, because you also have a weight matrix in your attention score, which is going to adjust things. It's going to adapt during the training. So the algorithm is actually going to push this attention score to be more and more important, and it's going to push this attention score to be less important.
Oh, okay, I think I got it.
Okay, cool. That's what we mean by putting attention on part of the waveform.
Yes, can I also just inject my understanding here? Because Sasha's question is exactly what I was asking you previously about the accumulative. So the attention score, if it is accumulative, then it's just like the integral. Then you look at the differentiation of the integral, you will find the peak, you will find the maximum change. And that's where you can find the time series that make the biggest change or make the biggest addition to the accumulative attention score. So, right.
Yeah,
so it's accumulative, but if you look at the change, you will find the most important cell.
Yeah, I think that's a very good analogy. Thanks, Rachel. Okay, I think we are already a little bit over time, so I will officially end this course. But of course, as I mentioned, I will stay here for questions in the office hour section. So if you want to stay and ask questions, please feel free to stay on the line. And if you want to leave, if you have other agenda, please feel free to leave as well. I will stop recording and I will talk to all of you next week.